Here we have a problem that leads to the solving of a quadratic inequality. Find a range of possible values of the function f of x equals x squared minus 5 over x minus 3, where x is a real number other than the number 3. X cannot equal 3 because if it did, we would have division by 0, which is not defined. Now, what does this question mean? Well, we can input any value of x into our function, any value of x other than 3. And when we do that, we will output some value that we can call y. So I'm going to replace f of x with y. So we're interested in all the values of y that are outputted from our function. Now it turns out that there are certain values that are not outputted from this function. One such value is 4. Actually, there are a range of values that are not outputted from this function. 4 happens to be part of that range. In other words, 4 is not equal to x squared minus 5 divided by x minus 3 for any value of x. Any value of x. To see why that is so, just for this one value, we can try to solve this equation. So I will pretend that there is such a value of x that gives us a value 4. I can try and solve this, multiply both sides by x minus 3. So we get 4x minus 12 equals x squared minus 5. Bringing this to one side, we get x squared minus 4x plus 12 minus 5, which is plus 7, equals 0. So I can try and look for solutions to this equation, values of x that give us a y value of 4. Well, we know that x is minus b, which is minus 4 plus 4, plus or minus the square root of b squared, that's 16, minus 4 times 1 times 7, that's minus 28, and all of this is divided by 2a, 2 times 1. Now you can see here that we have a negative value inside the square root sign. We get 4 plus or minus the square root of minus 12 all over 2. So there are no real solutions. Well, there are complex solutions if we go into complex numbers, but that's a different section. We're only interested in real numbers. X has to be a real number. The square root of minus 12 is not a real number. No two numbers the same multiply to give minus 12. So our x values, there are two of them, when we take plus or minus, are not real. As a matter of fact, this is a complex number. Well, we have two complex numbers actually. One complex number is 4 plus root minus 12 over 2, and the other one is 4 minus root minus 12, all divided by 2. So that tells us that 4 is not part of the range of the function f of x, this function. As a matter of fact, there is a range of values that are not part of the range of f of x. One way to see the range of this function is to look at a graph of this function. Now, this type of function is called a rational function, and I will cover how to graph these in another section. For now, I will look at a graph of it here. This graph has a break or a discontinuity at x equals 3. Remember, this function is not defined at x equals 3 because we have division by 0. So at x equals 3, which is about here, we have a break. You can imagine a vertical line passing through x equals 3. That line is known as a vertical asymptote. The function comes in two sections, or the graph comes in two sections. This section up here and this section down here. By the way, they continue on. But the thing is, the graph never crosses a vertical line at x equals 3. This vertical line here. Here is a rough sketch of the function. We have a vertical asymptote at x equals 3. So the graph approaches it. That's indicated by the arrow. It approaches this vertical line but never crosses it. Similarly, for this section of the graph, we also have an oblique asymptote. The graph approaches that. Both sections of the graph approach it but never cross it. You can see that there are certain values of y that do not correspond to any value of x, like y equals 4. See, if we go across if we draw a horizontal line through y equals 4, we will not meet the graph, which means that there are no solutions to 4 equals x squared minus 5 over x minus 3, as we saw earlier. It turns out that for all values of y ranging from 2 up to 10, there are no corresponding values of x. So there are no solutions to this equation. As a matter of fact, at y equals 2, there is just one solution. And at y equals 10, there is one solution also. Just one solution. But for all other values of y, there are two solutions. The range of values of y is actually the pink region. Because if we pick any point in this pink region and draw a horizontal line, we will meet the curve in at least one point. As a matter of fact, we will meet it in 2 points, except for at y equals 10, where we just meet it at 1 point, and at y equals 2, where we just meet it at 1 point. So if we pick any other point, like here, and draw a horizontal line, we will find that we have 2 corresponding values of x. So the range of our function is all the values of y that are greater than or equal to 10, and all the values of y that are less than or equal to 2. Now let's see how we can work this out without referring to graphs. What we do is rearrange our function to get x in terms of y. So we want to see what values of y will give us real values of x. We're after real values of x. You will see that certain values of y will lead to the square roots of negative numbers, like what you saw when y was 4. It led to the square root of a negative number. So x was not real. We couldn't find any solutions, real solutions corresponding to y equals 4. So we start by cross multiplying. We multiply both sides of this by x minus 3. So we get x minus 3 times y equals x squared minus 5. Now we want to get x in terms of y, but you see we have an x squared term and we have an x term. So we'll have to get a quadratic equation in x. We can't just make x the subject of this directly. So multiplying y into this and bringing xy minus 3y across to the other side, we get x squared minus yx plus 3y minus 5 equals 0. And we have to solve this quadratic equation to find out x. We will have x then in terms of y. Here we have x in terms of y. There are two expressions for x depending on whether we take plus or minus. Let's just check through this. For this quadratic equation, a is equal to 1, b is equal to minus y. What is c? C is all of this here. Doesn't involve x. Okay, so we call it a constant term normally. Well, it's not really constant here. Constant in the sense that it doesn't involve x. See, we're trying to get x in terms of y. So we plug these in for a, b, and c. So we've minus b, or minus minus y, that's plus y, plus or minus the square root of b squared, which is y squared, minus 4ac. A is 1, c is 3y minus 5. Simplifying inside the square root sign, we get y squared minus 12y plus 20. So here are the two expressions for x got from taking the plus sign or the minus sign. As a matter of fact, this first expression for x corresponds to this part of the curve. As a matter of fact, if we plug 10 in for y and calculate all of this here, we get x equals 5, this value. This other expression for x actually corresponds to this section of the curve. If you plug y equals 2 into this, you will get x equals 1. However, if you plug, say, 4 in, which we saw earlier, what you will get is 4 plus the square root of 4 squared is 16 minus 4 times 12, 16 minus 48 is minus 32 plus 20, minus 12, get the square root of minus 12. Of course, it doesn't matter which of these you plug it into, you get the same here. You get 4 minus the square root of minus 12 over 2. So this is not a real number because the square root of minus 12 is not a real number. Both of these, this number is actually a complex number, and so is this. So as I explained earlier, there is no value of x corresponding to y equals 4. So you see, we can't just have any value of y in this. Certain values of y will make this negative, and we can't get the square root of a negative number. So in order to ensure that we do get values of x that are real, we must have that y squared minus 12y plus 20 is greater than or equal to 0. It must be positive or 0. And it will be positive for values of y greater than or equal to 10 or values of y less than or equal to 2. So we need to solve this quadratic inequality to show that. So how do we solve a quadratic inequality again? Well, we start by solving the quadratic equation y squared minus 12y plus 20 equals 0. So we just consider the equation. So we forget about the greater than. If we factorize this expression, we get y minus 2 times y minus 10. We put each of these factors in turn equal to 0. If we put this equal to 0, we get y equals 2. And if we put the other factor equal to 0, we get y equals 10. The next thing we do is look at the graph of y squared minus 12y plus 20. Now I'm going to call this expression h. I can't call it y because the independent variable is y. The independent variable y goes on the horizontal axis, so this might be a bit confusing. Normally you see x here. Our dependent variable is h, so I have a sketch of the function h equals y squared minus 12y plus 20, and we're interested in seeing where h, this is h here, where h is greater than or equal to 0. So for what values of y is h greater than or equal to 0? So we're interested in the values in points on the graph that have h greater than or equal to 0. Well, it's all these points here. Pick this point here, h is positive. Similarly for this section here. So what values of y correspond to these sections? Well, if we take all values of y less than or equal to 2, 2 is included, or all values of y greater than or equal to 10. So the solution set of our inequality consists of these two regions. Of course, values of y lying between 2 and 10 correspond to values of h that are less than 0. If we take a point down here, the h value of this point is less than 0. That's where this thing is negative. That's what we don't want. So this region here corresponds to this region here. It should be the same length as this region. Scales are different. It's going from 2 to 10 here, and it's running from 2 to 10 here.